In this video, we will be working on a inclined plane problem again. Previously, we have been working on a block sliding down from a frictionless inclined plane, and we know in that problem, only gravity has done work, so the mechanical energy is conserved. Well, in this problem, we make the surface of the inclined plane rough. So we need to consider the kinetic friction in this problem. Because the friction is non-conservative force. So the term WNC, which is the work done by the non-conservative force, is no longer zero. So let's see, in this scenario, how do we find the final velocity at point B? Okay. So our setting of the inclined plane is the same as before. The height of the inclined plane is h, and the length of the inclined plane is L. The only difference is now we need to consider the kinetic friction of the surface. So the mass of the block is again m, and it's gonna start from at rest and slide down from A to B. So first of all, let's look at the kinetic friction. And to find the kinetic friction, let's first draw the free body diagram. We have the gravity, that is mg, the normal force, that is perpendicular to the inclined plane, and the kinetic friction, F of k. So we can set up the x and y axis along the inclined plane and perpendicular to the plane as what we did before. So now let's find the kinetic friction. So it equals to the kinetic friction coefficient multiplied by the normal force. And we have been very familiar with the fact that the n equals to the mg cosine theta. So we can directly write down the kinetic friction. So let's now look at the work done by this non-conservative force. So we need to multiply the friction by its displacement of the block. And here, the negative sign is because the friction and the displacement are along the opposite direction. So it gave a negative sign indicating the non-conservative force is doing negative work. So we will find the work done by the non-conservative force is negative mu of k multiplied by mgl cosine theta. So we know that when the non-conservative force has done finite work, then it's gonna cause change in mechanical energy. So it's gonna equals to the difference between the kinetic energy at the final state versus the kinetic energy at the initial state. That's the mechanical energy change. So because here we need to define the gravitational potential energy, so we need to set a reference point. So for simplicity, let's just set the ground as our 0 point of gravitational potential. So now we can write down each term in this equation. So on the left side, we have the negative work done by the non-conservative force. And on the right side, the final kinetic energy equals to half mvb squared. And because we set the ground as our 0 point of gravitational potential, then the final gravitational potential should be 0. The block slides from at rest, so the initial kinetic energy is 0. And initially A is h above our reference point, so the potential energy should be mgh. So with this equation, we can find the symbolic expression of VB, and here we have both H and L in our equation. If we want to further simplify this, we can apply the H equals L sine theta, so that we can obtain our final answer here. In the lecture, I gave a question for you to think about. That is, can we use the kinematic equation to solve this problem? And is this consistent with the energy perspective? So let's look at this question again, and this time we're going to try to use the kinematic equation to solve this. So again, let's look at the free body diagram, and the Cartesian and the x and the y axis is also defined as what we did before. So with this setup, we can write down the Newton's second law along the x and y direction. So along x direction, we have the projection of mg. That is along the positive x direction. Its magnitude is mg sine theta. And we have the kinetic friction, f of k, along negative x direction. That is the total force along the x direction, which gave rise to the max. Okay. Well, along y direction, we have the normal force along positive y, and the projection of mg along negative y. The magnitude is mg cosine theta. That's the two Newton's second law equation we can set up for this scenario. So again, let's replace mu of f of k with mu k times n, so we can obtain that the mg sine theta minus mu of k mg cosine theta, that equals to max. So we can divide m from both sides, then we can obtain the acceleration, that is ax, along the slope. So now we can use since we already find the acceleration, we can use the kinematic equation to solve this problem. So we know the initial velocity, v of a, is 0, and we know the total displacement from A to B is L, and we also know the acceleration. Now we want to find the final state v of b. So the most efficient way is to pick up this equation. So vb squared minus va squared equals 2 times a times displacement. So let's plug in the values we have. So va is 0, and a here is ax. Here is ax, and the displacement delta x is L. So with this equation, we can also arrive at the final velocity vb, and it is exactly the same as what we find from the perspective of energy.